I may be mad. I may be crazy. I may even be a fool. Not even an astronomer, cosmologist, or physicist, though a budding poet of sorts. No equations do I ever attempt to write, possessing incredulously heightened senses of imagined curiosities. Universe formed in three primary divisions: known, ordinary matter, dark matter; unknown, invisible, dark energy, unseen by the naked eye. No scientific explanation to date given. Given my perspective, light and dark matter, defined by Einstein's theory of relativity equation, E equals mc squared; dark energy, the opposite of manifested reality, the illusionary materialistic universe, unmanifested collective spiritual energy, not seen, though spoken about, since time memorial, substantially infinitely smaller than the configuration of the essence of soul, dynamism linking the astral body, mysterious abilities used in telekinesis, infinitely more elegant than perceived, dark energy. A simple explanation of the expanding universe, integral issues regarding density, a soul descending into the materialistic, manifested illusionary plane of reality, a new entity, a new spirit born, filling the vacated emptiness, an old soul in ascendance, the death of a symbiont host, ascending spirit, no new soul born, a universe of intrinsic values, beauteous mathematical bounties. I may be madder than a hatter, crazier than a lunatic, whatever that may be. Darkened skies infusing, looming over me, bringing a smile, or two perhaps, to a respectful but amused scientific community. But what if my careful spiritualistic imaginings are right regarding dark energy? All right, that was a
Wow.
random mishmash of, I don't know what you call it, but somebody called Clive Norman on January 31st, 2019, which, by the way, not January 31st, July 31st. Um, so, yeah, only two.
Matter, madder than a hatter.
It seems like it, right? I mean, um,
I didn't
but
think it was that bad. I thought it was quite good, actually.
really? Okay, who is this voice? Who's this voice?
Wait. What is this? What are we watching here?
Okay. All right. So there's two things, right? What are
Yeah.
we watching here, and who is this? Okay. So let's bring Leonard. Hello. You're talking,
Muting.
but no one hears
Muting. Yes. Muting. I'm unmuted now.
you. Okay.
Presumably.
You are unmuted. Nice headband.
Thank you.
It has been a many weeks. I was gonna say many moons, but that would mean months. Maybe it has
That's
been
right.
one moon, one turnabout of a moon.
Yeah.
So glad to be back. This
How are you
is
doing?
Oh, okay, that's right. I first need to talk to Leonard to answer your question, and then I will address the audience, right? So I will say I am doing all right, all things considered. There's been some happenings in the last month, and so I took a unexpected break, and then Leonard, I know you were out in New York um, one week, and then I was like sick last week, and so it just ended up being a whole month. So to my audience, slight apologies,
We
but
we
glad we're
beg your
back.
forgiveness.
Yes. The people 10,000 years in the future probably doesn't care at all.
Yeah, they don't. It's an infinitesimal amount of time for them.
Right.
So right.
Yeah.
So
But for those who do watch it live, though, we are back. This is SG2 Space episode 208. So I have the scrolling ticker on the bottom. So as always, thank you to our supporters and patrons: Kyle Baker, Sam Welsh, John Graves, and of course I always put Atrin Rod there for helping produce the show for a while. And if you want to support it, you can go to patreon.com/SG2 on space. And of
yeah,
course,
leave.
if you're watching
Yes.
this,
What is it? Subscribe, share with your friends,
yeah,
leave
hey,
comments.
yeah, share
You
with
know,
friends, leave comments, the normal good
ask
stuff that
questions.
anybody ever does, right? I mean, to be actively engaged, so that, right? So, with all that said, um, let's
Well,
actually talk about the main thing today.
yeah. And what
Which,
was that? What did you want to talk about? I forgot. I
well, you said the dark matter story. There was
Dark matter. Oh yeah, dark matter. That's a good topic.
yeah. So this is the name of this episode, the dark matter story.
Oh, okay.
So,
Right.
what is we talked about this before in that poem I just put up. Here, let me see if I can do it. Like this talks about dark energy some, but we're not going to that. In fact, actually, the poem I just realized is called Dark Energy.
You know, dark energy is something different from the dark matter.
Okay.
Although I have heard people say that dark energy is a form of matter. So but anyway, let's get started with this. I mean, I think we just wanted to confine our discussion to dark matter. Dark matter is a form of matter that we think we're quite sure exists. It's a form of matter that doesn't interact with light or with it doesn't appear to us sensibly through interaction through the electromagnetic field. But it does seem to manifest gravitationally. And I guess historically, the first.
Let me interrupt you a second.
Yeah.
When we say dark matter, it's not that it's actually dark, right? It's just that.
Yeah. That's a thing. It's not black. It's not something that's black. Yeah. So it's actually like invisible.
Okay, it's
right?
invisible. So really, if you want to be perfectly, well, not perfectly, I guess more scientifically accurate, you could say, like, they should have called it invisible matter. But
yeah, they should have said invisible matter or transparent or something like that.
Right,
and I think a lot of people don't really understand the profundity of the issue scientifically because
go on with the profundity.
Yeah, the thing is, I think most people hear, they read about it on, in the clickbait articles about dark matter. So, oh yeah, well, there's something dark out there. Okay, big deal. But the thing is, it's not just that. It's that it makes up most of matter, and I think of all of the things that constitute the universe. It overwhelmingly dominates the amount of gravitating material that exhibits gravity, but we don't know anything about it. We're starting to form some inklings or some ideas about what it might be. And so historic
85% of the universe for matter.
Yeah, that's right. And so the sensible, what they call baryonic matter, or the stuff that we can see, makes up about 4% of everything else, and if you include dark energy in that as well. Let's do dark energy another time. So, and it does sound cool. Yeah, that's true. So,
Alicia says it sounds cool, which I completely agree with. Go on.
So, anyway.
All right. How do they know that? Okay, if it's completely transparent and it's not dark, how do they know there's something there?
Well, I was going to mention something about the history of how this was discovered, and there was an astronomer named Fritz Zwicky, okay, and don't hold me to this, but I think he came from Europe, from the old country, in the 20s and 30s, and he settled in California, Stanford, and he was an astronomer. And he was using this thing called the virial theorem, which means that if you think about what?
Virial, like
VIRIAL, virial theorem. And so what he was doing, he was making observations initially of a cluster of galaxies. In other words, he could see them through the telescope, and he could see there were a whole bunch of galaxies, and they were sort of gravitationally bound in a kind of cloud or a cluster. And so he was able to use the redshift, blue shift velocity measurements and determine how fast these things were going, and then calibrate the amount of matter that was present in this coma. What it's called the coma galactic cluster, and so he said, wow, it looks like these particles, these galaxies are going too fast, right? And it's not just like 5-10%. It was like there was like the amount of visible matter that was present was less than he needed like 400 times more mass present to account for the amount of amount of kinetic energy that was being expressed by the um, stars in this cluster, and published that, and actually he coined the term dark matter in German. It's like, I think you say dunkel. I'm gonna dunkel materia
This
was
is the
what
guy, by the
he
way,
called.
if anybody knows,
I
Chris Zwicky at the Schmidt telescope
yeah,
in the 1930s. And that's to get,
yeah.
I don't know. There you go.
And
Yeah.
so this is, he it was enabled by technology and ability to take long duration exposures and measure the redshift of of astronomical bodies. And so he said, his publications in that era were saying that, look, there's some dark matter there, right? And nobody really paid very much attention to it. I think most everyone assumed that it was dust, or there had to have been some prosaic, um, explanation for it. And it wasn't, it was known for some time, but nobody else made much much of it. I remember, like, as a teenager, hearing about this, reading about it, and yeah, there it is. Hey, there, dunkel materia. I see the word dunkel right there. So
Wow. It took like over 40 years for it to be accepted.
yeah, and actually, it wasn't really accepted until the late '60s, early '70s, with the work of Vera Rubin. I think that's her name, Rubin.
Right. Yes.
And
That's
she
what
was
you
collaborating. I think maybe she had a graduate student or somebody named Ken Ford, and what they did was they were working on spiral galaxies and doing the same kind of measurements of velocities in rotating galaxies.
Let's put this person up.
About
Vera Rubin.
Vera Rubin. Incidentally, there's a company called NVIDIA. This is a little bit of a sidebar.
Is NVIDIA like the graphics card company?
Yeah, they make GPU, graphics processing units, high performance computers. Okay, they're going to release a new processor in the next month or so, and it's called the Rubin.
Is it named after Vera Rubin?
And it's named after Vera Rubin. Yeah.
That's astounding. To get a graphics card named after you, I guess.
Right. And she had a lot of problems with a lot of obstacles in her career. I think they were at Cornell or
Princeton does not accept women in Australia. That's wow.
Yeah, it's nasty. It's nasty. I'm definitely not up for that. Okay. So in the spiral galaxies, she was saying they were looking at the amount of how fast they were rotating around. And they were rotating much faster. It's the same story. They were rotating much faster than could be accounted for by just gravity, just gravity being there. And I just saw a note. Somebody said they love NVIDIA.
Invest in their stock. Hey, I'm trying to get audience participation, and people I tell, they just put things up there.
Matthew, yeah, I agree with that. I agree with that. Invest, but let's wait for a pullback.
All right.
Okay.
Agrees with it. All right, go on.
So the stars in the galaxy were rotating much faster, and then could be accounted for by the mass that was present. And that started to become like a thing, and so they really did realize that there was a big problem with too much mass in these galaxies. And actually, I can tell a personal story. When I was in high school, and I want to say it was about probably 74 or 75, I went on some like a summer camp kind of thing at the University of Maryland, and there was a professor there who was he was he had us working with that stuff. I remember he had radio. I don't. They were radio wave observations of velocities in the galactic arms of the Milky Way, and he had us, plotting the speed versus, other parameters. That was like a high school, those like high school camp things
Yeah.
for, that. So I remember doing that. So it had something to do with it. The professor's name, I wish I could remember his name. He was old then. I'm sure he's gone. But and he had a graduate student. But anyway, so that was the thing. And then in the 70s and 80s, people started. Well, no, actually, up through the 90s. Then there was more study of the microwave background, which we've brought up many times. And there's numerical modeling of the variation in the temperature of the cosmic microwave background, which is which is the noise, the light that's been.
So just to confirm something, is a cosmic microwave background, does that distribution like prove in any way dark matter?
Yes, so there is a characteristic of it.
Okay.
It's a black body. It has a black body spectrum, which is quite remarkable because it means that, to very high accuracy, it's the same distribution no matter where you are. And so you have one part of the microwave background surface, which is sort of it's like the remnants of the fireball that was the Big Bang, that we see vastly redshifted to microwaves, so it's just above absolute zero, so it's very uniform throughout, but there are very small perturbations in it which are attributed to the background field fluctuations. So, but impressed on top of those is a spectrum. So the size, yeah, here it is. There you are. So the size of these light and dark areas.
I'm going to quote this. The amount of dark matter in the universe before galaxies formed can be determined from a study of the fluctuations in the cosmic microwave background radiation. That's pretty interesting. All right, go on, Leonard.
Yeah, no kidding. Yeah, this is physics is just phenomenal.
Yeah,
the kind of things. But these variations, and you can see a few of these like variations. You see a dark area and then a brighter area. The scale of those can be characterized by a kind of spectrum. Like I don't want to use any jargon, but it's like, if you know what like Fourier or spherical harmonic expansion. So you have all these periodicities. So the scale of these fluctuations have been modeled. People have models of how this will expand and appear, and it relies on a very large amount of primordial dark matter. Effectively, a background. There needs to be a lot more matter present in order for this this variation to appear. And I think we've talked about it before, but so really these variations are very greatly amplified on an extremely uniform background. Really it would, on a normal scale, if they didn't amplify the variations, this would just be a uniform color all the way across. And some people are probably looking at this and wondering what this is. So I guess I should back up a little bit.
But we assume somehow everyone already knows what the cosmic microwave background is.
I don't want to do that. I mean, it's like so this is a global picture. So they stretched it out onto an oval like that. But if you would imagine that this would be over a globe, and we'd be in the center and looking in every different direction, and it's been stretched out to to show us the entire sky. This is what the sky looks like in the microwave, and this is interpreted as a surface that is 13.7 billion light years away, and it represents the time when the universe transitioned from like a quark or like a plasma to clear space. So it's the moment when the universe became transparent.
So just for everyone's reference, you cannot see, well, optical telescopes, which is not optical, I guess, like stuff that detects light. Let's put it that way.
Anything that relies on electromagnetic spectrum, which is light, infrared, ultraviolet, X-rays, gamma rays, and microwave.
Everything that we use to really observe the universe and to communicate with each other.
So this is the boundary beyond which we can't see with light of that form. We should be able to perhaps see gravity, because we're detecting gravity waves now. So we should be able to observe gravity waves. Somewhere behind this is a singularity of the Big Bang and all kinds of mysteries. We're talking about dark matter, but the point of this is evidence that was developed in the this was observed in the 90s, in the 90s and early 2000s of the 21st century. And that a model of the variations, the scales of variations, requires a lot more mass, a lot of dark matter than is present in the baryonic matter, which is like baryonic matter just means the matter normal matter that we know about.
So baryonic matter is a fancy way of saying the familiar matter that we all
the stuff that we can see.
This is I'm baryonic matter. Well, I'm made of baryonic matter, right? And so is everything.
We all that's not much of a distinction though, because so is everything else. Right. So
go on.
I mean you can try that line,
Well, okay. Well, okay. So everything that is not dark matter, like neutrinos, photons. Okay, I don't know why this says atoms, but like whatever other things, these are all baryonic matter. That's
yes, right. I would consider neutrinos and photons also to be sort of baryonic matter. So I mean, part of the matter. Everything, even energy, has a gravitating component. But this dark matter is important, and you can see the pie chart there kind of like shows you that we need a whole lot more dark matter in order to match. Yeah, we need a lot more, and that's pretty persistent. That's what we think is present today. And so the other thing that was being observed during the 80s and 90s was gravitational lensing. Okay, I'm changing subject now. So this is more evidence of that there's dark matter.
So gravitational lensing.
Gravitational lensing. So according to Einstein's theory, which is well established, the gravity represents a curvature of space-time. And so what it means is that when there's starlight, when there's a ray of starlight that grazes along the edge of a gravitating body, like I guess that's like a galactic cluster of some sort, that the starlight will be bent, and it'll make the star. Here's the telescope looking at some kind of object, and so it'll see in this case there's a galaxy that its position appears to be disturbed relative to where it really is. And starting around, I don't know, 1990-ish, 90 maybe, well, a lot with the Hubble telescope, and in fact, that is the Hubble telescope. That telescope, sort of cartoon there.
That might be the Chandra telescope, actually.
Oh, it is?
Yeah, I mean, this is from the Chandra website.
Oh,
Chandra
okay. All right, okay. But it's really it's a cartoon. It's a cartoon.
Yeah.
So,
right,
and
what are we
this kind of lensing.
Are galaxies going on now? No, go on. Sorry.
Okay, well, in the cartoon there, The real galaxy is between those two images.
Right
So
here.
so that's the real galaxy, and what
Real.
but it appears to be at a distorted position, and that's what it's showing by the two alternate images. Then, if you look carefully, there's a little dotted line that goes all the way across to this telescope. So the telescope sees that galaxy at a different position than from where it really is. And then I think if you slide down a little bit, can you slide the image down?
Slide down.
So
actually is the real image. This was graphical. This is real.
I think this is not the best that I've seen. I have seen gravitationally lensed galaxies or images where the entire an entire ring is formed of the image from the galaxy. So if you see a galaxy that is far away and then there's a gravitating mass in front of it, it will distort and stretch
if I can
out.
find a better picture then. But go on.
There should be. So that's very strong evidence, and that kind of evidence started appearing really in the mid 90s, I guess, right about the time that Hubble scope was was appearing in vogue. I was sort of wanted to say. Yeah. It still is. It's still a remarkable instrument.
This might be a better one. Look at that. Can you see it? Can you see gravitational?
Yeah. Okay. On the left side, if you look carefully, you can see some of the objects are like little streaks. You can see some of the objects are elongated and streaks, and I think that's the gravitational lensing effect that we're observing. On the right side, I don't know what we're looking at. It appears to be the same image,
but view is visible light with odd-looking blue arcs appearing among the yellowish galaxies. These are magnified and distorted images of galaxies located far behind the cluster. The right image has added blue shading that indicates the location of invisible dark matter.
Okay, so what scientists have been able to do is they've been able to use math to try to infer the density of this dark matter that's present, and so we're seeing a lot more gravitational lensing from this effect than we expect, and we can even use it to infer to sort of see the dark matter in ways that where it otherwise wouldn't be. We can virtually see it from its effect on the matter that the light that's passing through it. And so I think people get the idea. I'm sort of inarticulate and I stutter a lot, I know, but
I mean, that's fine. Here's another. If anybody goes online and looks at it, I mean, you can easily find numerous images that shows gravitational lensing.
Yeah. So this is more evidence that there's something really profoundly wrong with our understanding of the presence of matter in the universe. Right. So a final thing that was observed is there's models of the filament structures of how galaxies organize on cosmic scales. I don't know if I have any. I don't really know what it is.
What that means? I have not heard of that.
Well, there's what did I wrote some things down. Stand by.
Oh, I thought you were gonna
cosmic micro. So there's evidence from the structure of the way galaxies organize on a cosmic scale that have been modeled, and this requires a lot more. It's like there's a yes, this is it right here. These are I think the image on the left is a model of
art on the right side.
So on the left side, this is a model of of how galaxies will organize in intergalactic space over billions of light years.
Wow, this website's beautiful. This is called mapoftheuniverse.net for anyone interested.
Yeah.
Look at that. That's
So the filamentary structures that are observed in the way galaxies organize themselves over very vast distances, billions of light years, has been modeled, or it's the way it has evolved and formed, and it requires anomalous amounts of matter that are cold matter that are not visible. And so this is inferred as further evidence that there's dark matter present. So one of the things, so now that can, so we can start talking about, what do we think this is? And there's been, a lot of discussion about, maybe it's maybe little black holes, like maybe there's primordial black holes everywhere, or there's just dark objects that that don't absorb, and this is pretty much ruled out because of a
Go ahead. No,
hi, Justin. Justin said hi.
I put Justin's comment there for much too long. Never mind. Hey, if you guys have a question, ask a question. Don't just say hi. Although I will put that up too. That's okay.
I think it's fine. I think it's fine to say hi. And in fact, I think I'm gonna say hi. But
it is fine to say hi. That is true. Okay. So we talked, just to not a recap, but yeah, actually, recap here. We talked about the discovery of not the discovery, but like the impetus that led to why we need to, I guess, have something more than just beyond the visible matter that we see. And we also talked about
these things that.
But what is it?
Right.
We're there.
So what is it? And so some people are thinking, well, maybe it's just like some dust, or I think in the 30s, to explain Zwicky's result, people just figured, okay, so there's a lot of matter there that's not. They didn't even. It wasn't even until about 1938 that people even had a clue about why stars were what it was that was burning in the stars, and so. I think they just figured, well, there must be something. It's interesting. It's an interesting observation, but there just is some dark material there that we can't see, and that maybe someday we'll be able to see it. But this has been kind of like as our measurements get better and our telescopes and surveys and so forth proceed, that's been sort of ruled out. There is the thought that there might be like black holes, like there might be like what they call primordial black holes. So before at the time of the Big Bang, behind that cosmic microwave wall, that there were lots and lots of black holes that were created. But there's been surveys. So from that, what we expect to do a survey of stars, and every now and then you should see like them sort of become. If there were black holes in the way, they would cause a very significant distortion of the background, and so we should see stars sort of winking in and out of the gravitational lensing effect from black holes or other objects that aren't there.
And observe that. Or
say it again.
Okay, continue.
What I was saying is that proposal has been tested and ruled out, because what we'd expect to see would be a lot of like the density of primordial black holes to explain dark matter would have to be great enough that we would see stars, we would see occultations of black holes, and they would do profound things to the starlight. In other words, the starlight would we would see stars sort of winking in and out of existence, and we'd see a lot of it, based upon the theoretical size of how much matter that would be needed to explain the dark matter.
Mhm.
Another popular candidate is something like a modification to Newtonian gravity. I forget
That is an
that.
interesting proposal.
So the idea is that there's something wrong with Newton's gravity, and in fact, in that case, Einstein's gravity needs some extra modification so that, in the Newtonian sense, for Newton, gravity is a force between two massive bodies, and it's proportional to the product of the masses, and inversely proportional. The force is inversely proportional to the square of the distance between them. Yada yada yada. Okay, so maybe there's something different at very great distances. So when objects are very, very far apart, maybe it doesn't fall off as 1 over r squared, as 1 over the distance squared, but maybe it's 1 over the distance squared plus a little bit, something like that. And you, in fact, you can formulate a modified gravity for things like the rotating
This
the
this
rotating
article says, okay, so these things are called MONDs, I guess.
Yeah, I think that was the acronym I was trying to remember. Modified Newtonian dynamics. Is that what it is?
Supposedly,
Mon-
this article
yeah.
says like, hey, that is actually not true, but who knows?
Yeah, and so what they did was they did some really careful observations of objects that are very far apart, the motion of gravitating bodies very, very far apart, and they couldn't make it work. Okay, and so I think this is pretty recent result.
This is
And so
2023. This particular, yeah, November 30th, 2023.
yeah, I never thought much of this Mond theory either, because there's an observation of there's several observations of colliding galaxies, or colliding galaxies, or colliding clusters. So you'll have two galactic clusters, and they will collide, and one of them is called the bullet cluster. I think you could probably find a reference to the bullet galaxy, or bullet, and so the interpretation is that the dark matter, which makes up most of the mass of these objects, they're both coming together like this, and then they interpenetrate, and then the baryonic matter interacts. There's gas and dust and that kind of thing, and they interact to the point where it gives off, you can observe it in X-rays. Yeah, that's it. Okay, so
okay, let me see here.
This is interpreted as two galaxies that have collided and penetrated each other. And if you go back up, I can describe the image there. Go back up to the image. It's interesting.
Go back to the image, which
so
to the untrained eye just looks like two colorful blobs and a bunch of galaxies. But go on.
Yeah, and so they use that technique for trying to infer where the dark matter is from the gravitational lensing of the background, and that's what the blue diffuse clouds are. That's the dark matter.
Okay.
Which I want to emphasize, we're not.
I was going to say these colors are artificially thrown on there. I just want to say that.
Yeah.
All right, go on.
Yeah, right. So I want to emphasize that we're not imaging the dark matter. We're inferring its presence from the way the background has been distorted. The background stars are distorted, and so people have developed computer codes that will invert those equations.
Mm-hmm.
And then the red is X-rays, and the X-rays are coming from the baryonic matter that kind of got dragged behind. So you can see it's as though two objects interpenetrated. So they collided and interpenetrated, and the dark matter sort of was not affected, was only affected by the gravity, and so they just sort of like pull apart. But the the physical matter, the baryonic matter, which is the red showing up in X-rays, has been left behind. So this is a case where we can see that an object that was made of regular matter and dark matter got pulled apart, and so that's the MOND. The modified Newtonian gravity wouldn't explain this in my mind. So I never. What?
So what would explain this? I mean, this would just
the baryonic matter is exhibiting other interactions, other than just gravity. They're like colliding and being affected by the plasma and so forth.
Okay, yeah, I see what you mean in that if dark matter was a type of regular matter, then it would have been affected by the fact that they're colliding with each other.
They're colliding with each other, and they would be interacting through electromagnetic interactions.
Normal matter doesn't interact. Right. So it's like hot gas and each are slowed by drag. In contrast, dark matter was not slowed by the impact because it does not interact directly with itself or the gas, except through gravity. Yeah. Okay.
That expresses it so much better than me fumbling around trying to.
I mean,
that's what I'm trying to say.
Articles, right? So, they probably spent hours trying to figure out what are the perfect words to put here, and then they summarize in this little abstract paragraph here.
We might be able to get ChatGPT to do even better than that. But I digress. So so that's one of the, we've kind of ruled out that MOND theory. And so there's been a couple of others. So I think pretty much we've settled on the idea that dark matter is some kind of particle, and it's not one of the particles that's in the standard model. But it may be related to something. So there is a particle in the standard model that has some of the characteristics that we're looking for, and that's the neutrinos. So now neutrinos are very interesting. They're sort of kind of neglected a little bit but because they're very hard to study. Neutrinos were inferred in the 1930s by Wolfgang Pauli. There was an observation that when a neutron, they were studying, they knew about neutrons. When a neutron will decay into a proton, it gives off you get a neutron, you'll get an electron. It'll emit an electron. It's called beta decay. And a proton can also decay when it's in a nucleus. Okay, a proton by itself doesn't decay, but protons that are part of the quark structure, sometimes that will decay into a positron. A positron will be emitted, and then a neutron comes out. So you can get both of those kinds of things. But what was happening was that the energy wasn't adding up, and so that was noticed in an article in the early 30s, about 32, 33. There was a conference. I'm not sure if it was in Italy or, well, it doesn't matter really. Does it matter where it is? It's just, but in the early 30s, Wolfgang Pauli, he didn't go to the conference, but he sent a letter that somebody read, and he was sort of like he was a kind of a dorky kind of character, and he addressed the conference as,
this was like a physics conference, right?
It was a physics conference, and he sent
a non-dorky character.
He sent a long letter, and he addressed it to "Dear radioactive people," and so he said, "I've done a terrible thing. I've inferred an idea of a particle which emits. This is to explain beta decay. Beta particles. So he says, got the the beta particle comes out, and then because people were saying, well, the energy is lost, it's not conserving energy, and people kind of thought maybe that's what was happening. But he said, suppose there was a particle that did not interact through the photons, through electromagnetic force or forces, and was carrying the energy away. And so, and at that time, they called that a neutron. So for a while, we had two different kinds of neutrons. And then the folks in Italy, Enrico Fermi, and he had a group, and so they were talking about it, and he said, no, it's not a neutron, it's a neutrino. Okay, so neutrino is like the diminutive form in Italian, and so that's what we call it today. So neutrinos are real things. They only interact through the weak force, and so there's three different kinds of forces that
so different kinds of forces.
Yeah.
Or is it?
Well, there's four different kinds of forces. I'm kind of leaving out gravity because
gravity
but the gravity is not in the standard model. So these neutrinos kind of fit the bill. But the problem is, for a long time, we didn't think they even had mass. And so some of the issues, so we can talk about neutrinos a little bit. The idea is that whenever there's radioactive decay, particularly the radioactive decay or any fusion process, fission process, you will get neutrinos out. And it turns out neutrinos are probably the most abundant particle in the universe, and trillions of them are penetrating your body. I think the apocryphal thing that you hear people say is it would take a light year of lead to shield you against half of the neutrino, to absorb half of the neutrinos in a neutrino beam. So they're very the other word is they use their ghost-like particles because they're so difficult to detect. But there have been techniques that exploit the weak force, that occasionally the neutrino will it'll do the kind of the reverse beta decay process, particularly with certain kinds of atoms, like chlorine will interact with a neutrino and give off a radioactive argon. And so we've built detectors that
coming back into dark matter world, so to speak.
Yeah.
Since I know you love to talk about neutrinos, but the audience might be wondering, why are we talking about neutrinos?
We're getting there. Listen, this is important, okay?
Go on.
So you're trying to guide me back, but I'm actually on task.
Oh,
so
you're on track. Okay, got it.
Okay, I am on track. Okay. It's just that the thing is, neutrinos are all left-handed. What does that mean?
I don't know. I'm right-handed.
So there's a characteristic of these things called fermions, where they have there's a word called chirality.
Okay?
Chirality, and it has to do with the direction of the spin relative to the direction of motion. And so all neutrinos that we are able to detect through these all exotic mechanisms are left-handed, because the weak force only works on left-handed particles. That's not quite true, because the neutrinos also have anti-neutrinos. There's regular neutrinos and anti-neutrinos. Anti-neutrinos are right-handed, okay, and they also participate in the weak force, okay. But the other characteristic of the neutrinos is there's three different kinds. There's an electron neutrino, there's a muon neutrino, and there's a tau part of tauon neutrino. So those are the flavors. You'll sometimes hear them talk about flavors. So each one of these particles has flavor, and they oscillate back and forth. And this was only discovered in the early 2000s, late 1990s and early 2000s, that the different flavors of neutrinos will oscillate because of quantum mechanical.
When you say oscillate, you mean they change from one kind of a neutrino to another kind of neutrino.
They literally change from one kind of neutrino to another kind of neutrino.
It would be like if I suddenly turn into Leonard and then later turn into myself again.
Yeah, well, right.
Okay.
And so and also all
weird. All right, go
all
on.
three of these regular kinds of neutrinos, they have different masses. And one of the things that one of the reasons we know they have mass is that it means that we originally thought that they traveled at the speed of light, which means they didn't have mass. We thought they were massless, and so there was this big problem with the sun. Okay, what was wrong with the sun? Well, the sun gives off neutrinos, and these were being monitored. It's a major source of neutrinos that we have, on Earth, and they will oscillate over a period of time. And so the explanation, there was this deficit of neutrinos from the sun, solar neutrino problem, which you can probably
Right.
Google.
The solar neutrino problem, where it seemed like the sun should not be having like that.
And
like,
yeah, there was a deficit. I remember reading about it, about the solar neutrino problem, and they solved it because they realized that there is this oscillatory behavior between the three different kinds of neutrinos. So an electron neutrino, which their instrumentation was all set up to detect, would turn into a muon neutrino before it got to the detector, right? And they're working with this like in at Fermilab. They've figured out a way to make a neutrino beam where they can beam it through the Earth all the way to a laboratory that's 30, 40 miles away, right? And so they're able to very carefully observe all these things. Okay, so that's not the whole story with the neutrinos. Okay, neutrinos fit the bill for dark matter, but they're not massive enough, and they're too hot, okay, to explain all the things I just talked about. But there's another thing. Okay, so another thing that happened in the 1930s. There was a scientist who worked with Fermi in Italy.
Mm-hmm.
His name was Majoramo.
I'm constantly amazed by how you remember all these scientists' names and can pronounce them.
His name was, I think his name was Ettore Majorano.
Is that
Okay, and so
Italian?
sometimes you can look up Majorano particle or a Majorano neutrino, because so he's very prescient, genius level mathematician. Let me do a little sidebar on him. He worked with Fermi and all of his other little friends, and then one day in 1938, he bought a boat ticket from Naples to Palermo,
Mm-hmm.
and then he was never seen again.
What happened to him? Okay, by the way, for everybody who doesn't speak Italian, how do you spell this guy's name?
Majorana.
All right.
Majorano.
Okay, here I found him. He looks interesting.
Looks like a nerd, doesn't he?
I mean, every physicist looks like a nerd.
He looks just like some people I work with, young guys I work with. Looks exactly
Did you
like them.
was
Yeah.
a
But he
younger
just
version of
disappeared
you
one day.
also- Okay, anyway. Oh wow, yeah.
No,
He
he
disappeared
no.
after participating. What? Okay, explain. Okay, is his disappearance related to his theories, or this is just a fun fact? That
No, it's not related to his theories, but it's sort of a tragic kind of thing. He had some kind of troubles. Something was bothering him. He had been in Germany, and Germany was doing German things in the 30s.
So interesting. Yeah, Germany was doing Germany things in the 1930s. Good way of putting it.
Yeah, and he may, I don't know. Nobody knows. I mean, there's all kinds of. I think they reopened a police investigation in some kind of forensic investigation in I don't know, about 20 years ago. There's some thought that maybe he showed up in South America somewhere. But nobody knows. He did leave a note. He left a note to his friend, says, I'm going away, and I'm sorry, and I apologize. And he did send a note from Palermo, but he was never. But anyway, let's talk about physics. So
I'll read his bio later. I'm sure it's very interesting. But let's talk about physics.
Yeah. So what he realized was that there's a different. Now we're going out onto kind of like very theoretical areas of this is really on the edge of physics right now. So being very speculative. There is the thought that there is not only the flavors of the different kinds of neutrinos, but there is a what they call seesaw mechanism
What's the
for
seesaw mechanism?
manifesting. Well, it means that there is some other particle that is. So we have the left-handed neutrino, and then we have a right-handed neutrino for a type of particle that is its own antiparticle, and that's where Majorano comes in, because he predicted that there would be such a thing. And the characteristics of the spin matrix, the matrix solution for the quantum mechanics, says that one of the particles will that the matrix will have two what they call eigenvalues, and one of the eigenvalues will be the left-handed particle, left-handed fermion, and then the other eigenvalue is the right-handed, and together they characterize a certain mass. And in order for the mass, if the mass of the one is very small, then the mass of the other one is very, very large. And so one of the explanations that's right on the forefront right now, we may even hear about it, in the next, I don't know, year or so, or couple of years, is that there exists postulate a characteristic Majorano conjugate to the neutrinos, which are extremely heavy, orders and orders and orders of magnitudes heavier, and that for every left-handed neutrino, there's a right-handed neutrino, and that they will oscillate back and forth, which would manifest themselves, as we would be able to see that. But if one of the neutrinos, so one of the things is that the measurements of the masses of the regular neutrinos that we're used to dealing with, the three flavors, we're actually only sensitive to the differences in those masses. One of those neutrinos could have zero mass or extremely small mass, and its conjugate, Majorano conjugate, would have tremendously large mass to compensate for that. And that could be that is a likely candidate for what the dark matter is. And
wow, that is really interesting.
Majorano,
named after it.
Yeah. Majorano, what they call sterile neutrino. Okay, so and so it's postulated that that this conjugate right-handed neutrino would be very massive and utterly devoid of even interacting with the weak force.
Wow.
We know that's possible because the weak force only sees left-handed particles. It only sees left-handed
sterile neutrinos, hypothetical particles that interact only via gravity and not via any of the other fundamental interactions, like what you said. Distinguished from ordinary active neutrinos in standard model, which carry an isospin charge of plus or minus 1/2, engaging weak interaction.
So
that is really interesting. I did not know that.
Yeah. It's too bad all of our audience has probably dropped off by now because
I don't think so. That's not true. Go on.
Right.
This is really interesting.
That's all I have to say. That's what I wanted to say.
So in order to introduce all this, we had to talk about dark matter, and we had to talk about neutrinos, and then how these particular neutrinos may be the reason, may be explanation of what dark matter. Right?
Yeah. And I found out about this by reading a book by Neil Turok.
One of your favorite physicists.
He actually is one of my favorite physicists.
Okay, see, I was not making that up.
What? Neil Turok, Turok.
I know. We did an episode entirely talking about him.
Yeah.
One time. A few months.
So I don't remember which book I read. I've read a couple of books by him, and I've seen some YouTube videos where he talks about it. And he's the one that turned me on to it, but I since have read about it in other places.
Well, this is
So-
somebody's random blog, but apparently this person talked to Neo Torok at a cafe, and he co-authored a paper.
Well, I wish I would meet him in a cafe.
Have you met Neo Torok at a cafe? No, you haven't. But you might.
No, nobody will see me. I no, I don't have enough. No, so, but yeah, and
So this
CPT
is
is
the article. Yeah.
yeah. So he mentioned that it's and so what I like about him is that excuse me. A lot of the problem, what I see, I think, is that physics has been on the wrong track through string theory, and that's starting to become apparent with the Large Hadron Super Collider. They found the Higgs boson, which was predicted 60 years ago. They found that. They made predictions of a whole bunch of other particles, that they were going to find these supersymmetric particles with the Large Hadron Super Collider
on the wrong track
in Europe. And so it's like a whole industry of thousands of physicists working on string theory, but they don't have anything to observe. So they're I think they're, oh dear, now I'm in trouble. So physics is on the but I think it's true. I think people, they string theory was okay up until when it was just talking about hadrons, protons and neutrons, and how gluons and quarks and that kind of stuff are connected together, because it resulted in things that you could observe. But people went too far with it, and they said, oh, well, if we can do it this, then what if we get really, really close? We go down 35 orders of magnitude closer, where gravity is important, then we can we can have like space-time, little strings that stretch across space-time, and the gravity and all that kind of, but there's nothing to observe, right? And so then they realized, oh, well, we need extra dimensions, right? Well, we can't see these dimensions. Well, the dimensions are all wrapped up, and so you end up with 10 to the 500 different solutions to your universe. So
yeah, agreed.
And also string theory didn't predict anything. String theory doesn't. You think a theory of everything would predict dark matter. Like.
But didn't you say like string theory is something which, like, you can literally use it to try to explain. You can use it to explain the things that you already know, but it doesn't predict anything new.
That's what I think. I believe that that's true. The string theory that for hadrons, the hadronic string theory that had to do with the quarks. The quarks are the particles that make up protons and neutrons, and they're held together with gluons. That's all good stuff, okay? Mm-hmm. But people tried to take that math and turn it into a kind of theory that would include the standard model with gravity, and they didn't produce anything that was observable. And in fact, it was a very rich mathematical theory, so it can do everything. It can predict anything. And so we end up saying, well, there's 500 different. Your job is to try to find. No, that's not true. I mean, so Turok is doing. Is I think he's back on track there, because
Neil Turok is actually doing real physics. Let me not. Is that controversial saying that? I don't know. You just said.
I mean, it seems to kind of. It does seem to kind of slip out from time to time. I don't want to offend anybody, and I.
You can work on theoretical frameworks your entire life that doesn't predict anything, I suppose.
But there, the clues that come out and say, well, there's 10 to the 500 different solutions. Well, that just means that that just means it doesn't. But Turok seems to be saying the right kinds of things, that speak to me. Saying, look, we want to keep it as simple as we can. We want to stay grounded in the observations that we can make. And so that's he's kind of one of my heroes. So anyway,
for anybody who's actually able to read physics, here's an article on that. The one that we spent about 30 minutes going over in terms of neutrinos, what it is, and then talking about this left-handed neutrinos, right? Did I get that right? Or is it right?
Well, the left-handed neutrinos are the ones that we can observe.
Oh, sorry.
Right.
These are
it's
right-handed,
that
theoretical neutrinos, which are right-handed. Yeah. Okay.
Regular neutrinos, that normal matter neutrinos that are right-handed.
Right. You can read this paper by Latham Boyle, Kieran Finn, and Neil Turok from the Perimeter Institute for Theoretical Physics and University of Manchester. So,
No, I think he comes from. I think
no. Neil Turok is Perimeter Institute. There's one co-authoring here from University of Manchester. So,
Oh, okay. Yeah, Perimeter Institute is in Canada.
Right.
Is Ontario.
So what kind of so for people who are interested, what kind of math is this? What do you have to do to understand
it's got a lot of squiggly lines and Greek letters. So
squiggly lines and
that looks a little bit like some special relativity with the A. So that looks a little bit like the Friedman equation.
I mean, the Lagrangian equation here. What is this? Is like some gravitational.
Yeah, G is usually the gravitational metric, the Einsteinian metric.
Gravitational metric.
Yeah.
I'm not sure what's okay. So this is a del operator on this. Actually, not del operator. This is a gradient, right? Yeah.
Yeah.
And I guess that's a complex conjugate of this. That's what I'm.
Yeah. So that should come out as some kind of scalar, and then he'll have those equations we call Euler.
Right.
What is it?
The equations
Euler
of
Lagrange.
Yeah. Spatial translations, spatial rotations, charge conjugate, parallel reverse, time reverse. Okay.
Yeah.
Charge conjugation, spatial translations. Yeah. Okay. So I think in order to understand this paper, you're going to have to learn some more physics and math.
I'm afraid so. Yeah.
I mean, I can't understand it.
Well, one thing when you enter a field like this, if you get the paper and you read it, right, and then you go, oh, I didn't understand anything, and then underline it and write in the margins and do stuff like that, and then get another paper and read it, and that's just like when his students go into graduate school, he'll probably give them this paper, and then give them a whole bunch of papers, and then if I'm learning a new field,
yeah, sorry, I interrupted you. Okay, how to learn
I was
this?
Saying, yeah, and in fact, in the old days, I used to take notes on the paper on note cards, or even enter it like in a spreadsheet. Later on, after I found about spreadsheets, I would make a spreadsheet with different columns, and then I would make like a little note about what that paper was about, and then I would build up a database of these, and so just the process of doing that, and you can eventually learn it. So you can learn more. One of the things is like Marcus Aurelius.
Well, it's
why am I talking about him?
I don't know. Wait, okay.
Because he always said one of the things that Marcus Aurelius said was try to do something that you think is impossible. Okay. So it's impossible for you to understand that paper, but
I mean,
you should try.
I do remember this from quantum mechanics in terms of it's like the broad ket notation. I don't know.
Yeah.
I don't know what operator is doing what. But annihilation operators. Okay, great. Not sure what that means. But hey, so in order to understand this research paper, you need to learn physics, probably quantum mechanics, probably
Yeah.
relativity it seems like it, since it has gravity in there, the gravity
Yeah.
metric. You need to learn definitely some calculus, differential equations, maybe.
Those look like spin matrices. Yeah. So you need.
Yeah,
Yeah. You need. This is a paper about quantum mechanics. Mostly.
it is, and quantum mechanics
And general
involve a lot
relativity.
of linear algebra as well. So
Yeah.
you need to learn that. Yeah. Okay. So and yeah, I have to say I have not done this kind of thing ever. So, but you know what? This is
What?
why you can just watch the show and have Leonard and I blab about it for a while.
It's fun. I enjoy
Without
it.
explaining what this is, as an example, whatever that is. I don't know.
Yeah.
Okay. But one day, assuming that I do take the time to understand this paper, maybe. Hey, actually, I just had a good idea, Leonard. Would it be interesting to like have one of our episodes to like dissect a research paper?
No, I don't want to do that.
Okay, never
Well,
mind.
sure. No, we'll do any. Yeah. No, I'm up for anything. Yeah, we can do that.
Okay,
But not this one.
not this one. This is.
I have some papers that I have some papers in mind that our audience might find amusing and interesting. We can,
This paper is a little too math and physics heavy here.
Right.
But yeah, okay, we can discuss that in terms of a future episode, because I was thinking I like the way that you talk about education as well, and how people can learn things, and how you learn it.
If you want to learn it, you get that paper and you look at it and go, I don't understand anything. Read it anyway, because you'll learn something. Interact with it, underline stuff, write in the margins. Write it in the margins. I don't. You put a little arrow next to it. I don't have any faintest idea what's going on. That kind of thing. And then read another paper and look at the papers in the references, and keep doing that. And you just keep doing that, and then you'll read a paper, and what will happen is, oh, I remember reading this before, okay, and then you'll go back to that paper. Oh, I see. And so little connections, gradual little connections will start to come together.
Little connections can form, even if at first you think you won't understand anything. That's very true. All right,
but I'm definitely up. I'm definitely up for doing stuff that you think is impossible.
Yeah, I think that we can talk about doing that sometime. Now, you realize this particular episode, I guess, is to make up for the fact that we haven't done an episode in over a month. This has been almost an hour and like half now, or an hour 15 minutes. I do want to talk about one of my favorite topics.
I absolutely do if you're up for it, but if you think we've been droning on too long, that's okay with me too.
It's okay. There's so much droning that it doesn't matter. This is you're not. I have not watched this video, but it's supposedly some extraterrestrial stuff. Let's see what we find.
It always is.
Okay. Here, let me see. What is this? Okay,
cemetery?
Do you see it? Do you see the alien? Here, let me go back. Let me go back here. Not that one. Okay, do you see it? What do you see?
I see headstones.
Okay. Let's see. I haven't seen this video, so this is the first time for me as well. But let's see if this.
I have some idea that there was.
What is that? That giant red arrow. That I don't look at that. That's a creature. That is a creature.
One of the women said it had an off-shaped body as well and was moving in rapid speed. The two women stopped for a while to view this creature, but then got frightened and left. I would hate to go by or to a funeral home and see something digging up people. I would be frightened too. So they were brave to have got this video of this creature. Now people check on your lost one's graves because this creature is still on the loose.
Okay, this guy's voice is annoying. So
yes, it is.
Here. What about that? Like that is. That's just like just you're in the woods and you just see that, right? Like I remember this video when it came out. Like
yeah.
Do you think it's real?
I
mean, and then what about that one? What about that flying bug thing? Like, what is that? Like, are you laughing?
No, never.
And then let me see. What else is this? Okay, let me see. Okay, some guy chopping wood. Is this just talking? Let me see if he's just talking.
One night he decides
Okay, yeah, I guess that
to
guy
investigate the mysterious sounds. This is what he caught on camera.
Okay.
I'm hearing the things in my woods again. I don't know if you can hear the noise.
Okay, I would not go out if I hear sound in the woods. Like, sure.
I've been hearing the sounds in the back of my woods. Quite a bit.
So he hears sounds in the woods. He goes to investigate.
What the heck is that? Oh my God.
Yeah.
The video shows some strange thing with large glowing eyes kneeling in the bushes. So is this some strange creature caught on camera? Is it just really good CGI? Or maybe a small, very thin person with excellent special effects makeup? You decide.
Astagfirullah, itu tuyul itu sebelah gym, tuyul. Itu belakang itu dari digiring sia. Di lo onita tuyul digiring sia tuyul.
Okay.
Eta digiring sia tuyul eta.
Tuyul is an undead in Indonesian folklore. Oh wow. Okay, so this is just strange things happening.
Tadi dinya belakang yang perkencang di.
Wow, so this happens somewhere in Indonesia. All right.
Yeah.
So it just showed like a bunch of random things happening here.
I see that. Yeah.
But I don't know if they're aliens, but it certainly was very creepy. So, of course, to Leonard's eye, this is all just absurd.
Or April.
It's like disbelief. It's like, okay. See, that's a problem these days, right? Like, you see something that you can't explain, and then you put it online, and then people just, like, assume, like, oh, it's just CGI, or somebody was just dressing up.
Well, yeah, there's nothing to, you can't believe anything, you know. So,
like,
I remember there was a newspaper called the Weekly World News.
Okay.
And it went for weeks, you know, showing, it was when George, the first
everything slowed down.
Bush alien that was meeting with, and they showed them on the White House lawn shaking hands, and the alien was like one of the Greys, you know, one of these. And I was in graduate school at the time, and I put them up on the bulletin. You know, I had a glass door outside my office, and one of the professors came by and said, he was English, a professor. His name was Dr. Dunning.
Okay.
And
I think
some people actually believe this stuff, you know, and
you're giving a story of basically this alien presenting himself in public, and some people believing it actually happened, when it was clearly a video that was made up.
By any reasoning sort of person, you know. So it's not like Men in Black, you know so they know where to go to find the aliens. You go to the post office, of course, because everybody in the post office is an alien. So.
All right, so Leonard's tip is, if you want to find an alien, extraterrestrial, you should go to a post office. You don't need to go to the woods or go somewhere.
I think we should call it a night.
Let's call it a night. All right, so hopefully people who watch this learn something. Don't care if you don't believe the last Saturday, just put there for fun. But hey, you know, if you do believe it, Leonard will probably make fun of you in that sense. For me,
no, I will never make fun of. I'm an alien myself. I'm a visitor from this planet.
Okay. I'm gonna end it with this to our visitors, not our visitors, to our viewers. from 10,000 years in the future, you probably already know everything. And so, nothing we say is new here to you. But I hope you had an amusing time watching early 21st century humanoids talking about things that you already know about.
Right. I'm a time traveler myself. I traveled here from the 20th century.
But you're traveling forward in time.
Yeah, and it was the long road too.
I mean, is there a shortcut? Probably not.
Yeah, no.
All right, everybody. This has been SG2 on Space, episode 208. Definitely extended episode. You can support the show on patreon.com/SG2 on Space. Been running the show for the last at least 3 years now. Leonard's been on for the last year and a half. And so thank you for all our kind supporters, Kyle Baker, Sam Welsh, and John Graves for your donations. Also, thank you for everyone who participated and been watching the show, whom I'm just going to throw out some names out there. Otis Burden. Wait, that is you. Okay, Alicia Baker. Okay, that's better. Matthew Lee, and Justin. All right.
Hi, Justin.
Who just put hi, and who actually tried calling me in the middle of the show. I don't know why. I guess he must have dropped off the show and assumed I was done too. Anyways, that's a complete aside. With that, we'll be back next week. Would be episode 209. What will we talk about? Who knows? It'll be something.
We'll think of something.
Right. Okay.
So anyway, good night.
Good night. Namaste.
Namaste. Shalom. Mwah.